All right, in the last video, we worked out how we could find the symmetry of the vibrations of a molecule by decomposing the reducible representation. But now let's actually ask and answer the question, what does that mean? How does that contribute to anything here? So to do that, let's look at the three vibrational modes of water. So when we think about this, again, we know there are 3n-6 vibrations since it's nonlinear. So therefore, we would have 3 times 3 minus 6, which equals 3 vibrations. And this is what those 3 vibrations would look like. We would refer to this as the symmetric stretch because the OHs are stretching in a symmetric fashion. They're in phase. Over next to it, we have the asymmetric stretch, because now we're still seeing stretching motions of those OH bonds, but now one is being compressed while the other is being extended. Final one here is the bend, and you should be familiar with these from probably Orgo, thinking about vibrations from, say, FTIR. So that's what we're going to look at here. So let's do the exact same thing that we did in the case of orbitals, but now let's do that for our molecule vibrations. So if I do nothing to the vibrations, I am still going to see an extension and a compression here of that vibrational mode. So therefore, I could assign it a character of 1. If I looked at a C2 rotation here, let's see what happens. I would bring 1 to this side, 1 to this side, but nothing has changed about them. They still look the same in terms of their motion. So again, a +1. First sigma V plane, which is there. So we're going to reflect the left to the right and the right to the left. So we would have, again, my vibrational motions looking like this. Well, those are some great arrows, aren't they? Again, nothing has changed in the way those look. They are still fundamentally the same. So again, +1 vibration. Finally, we have the other sigma V. This is the plane of the rotation. So again, if I do this out, my vibrations look unchanged. So finally, we have a +1. So let's look at the symmetric stretch for a second. So the representation for this vibration, for the symmetric stretch, would be 1, 1, 1, 1. And if we were to look back to the character table for C2V symmetry, we'd see, or we could recognize just from the values here, this would be an A1 symmetric label. So in other words, we're saying the symmetric stretch has A1 symmetry for that vibration. Let's see what another vibration looks like. So now we're going to look now at the second mode here, which is, again, our asymmetric stretch that we were going to look at. And we'll see what happens when we do our vibrations here to see something slightly different. E, as always, looks the same because we're doing nothing. So I'm just showing the displacement vectors now of those OHs. So we get a +1 for the E. If we look at C2, though, as a rotation, now let's look what happens. Now I have the downward displacement this way and the upward displacement that has moved to the other side. By doing that, now I have changed the phase of my vibrations. It gets a -1. If we look at the reflection symmetry down this plane, what do we have? Well, the left-hand side goes to the right, and the right-hand side goes to the left. And looky there, again, we've reversed the phase of the vibration. It gets a -1. And if we look at the final case here, this is the plane of our molecule. This does not change the phase of our vibration, so it gets a +1. So in other words, for this vibration of the asymmetric stretch, what we'd see is 1, -1, -1, 1. And if we were to go to our character table, we'd see that this is a B2 vibration. So now we're at the point we can do the same things we did with orbitals with vibrations. It's just telling us about the symmetry. How does that vibration transform with each of the symmetry operations of that character table? So that's what this does. And we can go back and forth on this. Here, all I needed to do was look at the vibrational modes to find out what the actual symmetry of that vibration was. And I think that's probably a good point to leave this video here. So it's just showing how we can see where that symmetry label now applies to the vibration. As always, we'll talk about this more in class. If you have questions, let me know. We'll get you cleared up. So until next time, be excellent to each other.